Hey guys, I want to talk about my family a little bit. Right here, this last little button. Here's a picture of them. So this picture is a little outdated, but this little girl here, she's 6 now. Lydia. Clara is 14. Gracie's 14. This little baby, she's 4 now. Eliza. And then Evelyn is 11. And Theodore's 9. Okay. So my wife and I have 6 kiddos, 5 girls. All right. Do Punnett squares say that we should have 5 girls? No. Okay. The probability suggests otherwise. Now this is my birth family. So my mom and dad. I have 5 brothers and 3 sisters. Okay. So 6 boys, 3 girls. Punnett squares don't predict that. Okay. Well, you can't really have 4.5. But how many of you guys are equal boys and girls in your family? Okay. How many? 2 and 2. 1 and 1. 2 and 2. 2 and 2. Okay. So your family's, it's as the Punnett square predicts should have happened. Okay. But now the question is what happened in my family just due to random chance, or is something weird going on? Okay. I had a friend in college. She had 7 sisters, and there were no sons in the family. So there were 8 girls, no boys. Is that due just to random chance, like coin flips, or is there something weird going on? Okay. And we do something called a chi-square test to figure this out. And it's statistics. It's statistically based. Okay. Chi-square, you have this equation on your pink sheet, but here's the equation for it. Chi-square, that's the Greek letter chi. Okay, page 74. Equals the sum of, you seen that weird symbol before? Add them up. Observed. Okay, the observed with my family is 5 daughters and 1 son. Minus expected. The expected with my family would be 3 daughters and 3 sons. Squared divided by expected. Okay, that's your equation. Let me take you through this other example with tigers. We all love tigers. Okay. Tigers are born, and 4 cubs, and 2 are albinos and 2 are orange. Okay. And Kristen, whoever Kristen is, hypothesizes that both of the parents must be heterozygous. Okay. So this is her hypothesis, this Punnett square. And Kristen is saying, yeah, okay, we would have, this Punnett square explains that little a would be albino tiger, right? And big A something would be orange. Okay, so Punnett square predicts 1 in 4 albino. Her friend Emily does not think so. Okay, you're dumb, says Emily, because only 1 out of 4 should be albino. But isn't 1/4 pretty close to 2/4? Maybe the difference is just due to chance. If you flip the coin 4 times, you get 3 heads. That can still happen. Okay. The only way to solve this is to use statistical analysis. We call this chi-squared. The purpose is to determine whether the results are statistically significant. Okay. You already have the equation. Okay. Here's what we would do with this tiger example. 2 orange tigers minus 3 expected from the Punnett square. Squared. Divided by expected from the Punnett square. We expect 3 orange tigers. Okay? Plus 2 albino tigers. minus 1 expected from the Punnett square. Square that, divide by 1. Add it up, you get 1.3 degrees. Okay? Now, on your pink sheet, you have a chi-square table right here. Here's that sheet. This chi-square table, I have some others on this PowerPoint. I want you to get used to this one. And then you also have your equation right there. And then basically over here, it tells you what everything means on the equation. So what we're going to do, remember that 1.33, that's our magic number, our chi-square value. And I have to figure a couple things out before I use this table. First of all, I have to figure out what the heck the degrees of freedom are. And that's just a statistics thing. And if you want to know the why of this, I have no idea. But if you talk to Mrs. Taylor, the AP Stats teacher, she can tell you all about it. Okay. But this is just statisticians figured out this table. And I don't know why these numbers are here, but they are. Okay, look right here. Degrees of freedom are equal to the number of distinct possible outcomes minus 1. How many outcomes for tigers? How many colors? 2. So all you do, you guys, is 2 minus 1. So we're going to use 1 degree of freedom here. And then put a little star here by 0.05. You're always going to use 0.05. 0.05 represents the p-value. And in sciences, that's the standard. What that tells you, it tells you that you're 95% confident. So it's like 1 minus 0.05, 0.95 confident. Okay, so 1 degree of freedom, 0.05. And that's my magic number, 3.84. Okay, so my number was 1.33. And my chi-square table number is 3.84. That number is, less than 3.84. So what that tells me is that it's the tiger colors are random chance. They're not there's nothing weird going on. It's just random coin flips. Okay. Now let's say your number was 3.9. Okay. If your number is greater than or equal to this number, then something weird is going on. Mutations, something like chemicals, genetic engineering, something weird is happening. Okay? This is a science journal. If you look in science journals, first of all, like if you look at the titles of these studies, it's just like over my head. Pregnancy imprints regulatory memory that sustains energy to fetal antigen. And then like the graphs on these, it's like, holy cow, graph craziness. But one thing I look for in these journals is, oh heavens, where did I find that one? Oh, proteins. Where's that DNA? All right. Okay, I circled it. Should have bookmarked it. Oh, you guys, check it out. Error bars. Yeah. Now look, some sign. I know what's in here. I know what's in here. I'll just find another one. Comet-like, blah, blah, blah. Man, oh, this is tons of genetic stuff in here. Oh, I found it. Okay. Woo! Okay, p-values, less than 0.05. All over in these articles, if I can find them, there's p-values. Okay? And what that p-value of less than 0.05 means, so if you reach this number, your p-value is 0.05 or less. And what that tells you is that there's a significant difference. Okay, there's a significant difference statistically significant. So I'm making my natural resources concurrent class do this too. They're doing something called a t-test. But let's say, oh, Jackson, how tall are you? 5'11". Okay. How many inches is that? 71? Charles? 5'9". 5'9". 69. Okay. And now I'm just going to make up some other heights here for guys. Okay, Maylee?
5'6".
5'6". Alicia? 5'4". Elizabeth? 5'4". Sam? 5'6". Let's just do all of you. Claire? 5'9". Ainara? 5'6". Okay. T-test. Calculate. Ah, look at this p-value. It's 0.0011. So that p-value is far less than 0.05, which means this difference is considered to be very statistically significant. Okay. If I surveyed guys and girls in junior high, maybe not, right? Okay, so if you were doing a science research project, okay, so let's say you're studying how many ants are in this habitat on multiple days and how many ants are in this habitat on multiple days. And if you just have the average, that tells you really nothing. Because the problem is when we just do average, we think it's different, more different than it really is. You need a p-value. And I probably get way too excited about this, but this number right here, you guys, is like the heart and soul of science research. Because what it says there is a significant difference between this control group and this experimental group, or there's not. So this is like your answer to your hypothesis right here. Okay? So anyway, we're doing the same thing here with genetics to see whether the genetic outcomes are really just the same as what Punnett squares predict, or if there's something weird going on. Okay. Okay. Back to 74. Do a little T-chart here. A couple other terms I need you to know. Hypothesis. You already know that, but I'm going to give you a little different definition. And then null hypothesis. You guys know what null means? It's like zero, like nothing. So we abbreviate null as H0. Okay? H0. When you do a chi-square test, you're either going to reject or accept this null hypothesis. Okay? Sorry, actually up here, degree of freedom. We need to add that. Or down below, I don't care. Degree of freedom, number of outcomes, -1. -1. Okay. So if puppies can have 4 different phenotypes, 3 degrees of freedom. Okay. Okay. The hypothesis in chi-square testing is this. The difference between observed, 5 daughters, 1 son, the difference between observed and expected values is due to something other than random chance. There's something weird going on. Okay? So it could be, like we said, it could be chemicals, it could be mutations in the DNA and the genes, it could be genetic engineering. Okay, something weird. The genetic outcomes are weird. Okay. The null hypothesis, on the other hand, the null is like the opposite. There's no difference. There's no difference. It's like the Grinch, right? There's no difference between observed and expected other than random chance. It's just due to the roll of dice. And in a genetic sense, the Punnett square explains it. So one way, I used to have this analogy with shoes bought from Walmart, and it wasn't the best, but something, maybe another thought that might help. In the null, there's nothing weird. Nothing weird. Weed. Weird. Okay, nothing weird in the null. Okay, so 3 steps in this process, and then we'll try some more. Calculate your chi-squared value. Now, guys, by the way, this is not x squared. This is not x squared. Never square root this. Never square root it. Sometimes, anyway, it looks like an x. It's not. Step 2, take that number you get. We got 1.33 in the tiger one, and see if that chi-square value is less than or greater than or equal to the critical value. We call that number in the table on the pink sheet the critical value on the pink sheet. And again, always use a p-value of 0.05. I don't know when the 0.01 would be used, but that would be like 99% confident. That's science. Science says 95% confidence. Confident enough. Okay. And then you have 2 options. You can either reject the null if you reach the number, the critical value on the pink sheet. So reject if you reach it. Okay. So on that first one, if we would have reached this number of 3.84, we would have rejected the null, and which would mean something weird is going on. Okay. Or you accept the null. And this is just a funny thing about science. In science, you never really accept the hypothesis. You technically can't say, my hypothesis was right. You say, my null hypothesis was, I reject the null. Anyway, it's weird. And I accept the null if critical value is, if the number is less than critical value. Okay, I accept the null, meaning null, nothing weird. Null, nothing weird. Okay, it's just random chance. Okay, grab your Chromebooks and go to page 39, please. I'm going to have you practice one with corn, and then we'll call it good. The rest later, but, it's called corn chi-square. Okay. And just a reminder, all these practice problems are due the 28th, so including the chi-square pages, of Friday. And that is also, that'll be test date for this unit. So. Okay, corn chi-square, you'll need this pretty little picture of Indian corn or whatever. So on Indian corn, you got 4 phenotypes here. You have, look, let's call this, if it looks like a raisin, it's going to be purple and smooth, or sorry, purple and shriveled. And then, even though this has like a divot in it, that'll be purple and smooth, any of those. Okay, and then you have yellow and shriveled, yellow and smooth, okay? If you guys can count those up to you if you count the back row or not, but count them up and record those in that table, will you? Let's start with that. I really need to get some real corn you can look at, but boring, leave the picture. So page 39, just get that on your table and yeah, see what we find here. I'm going to go back to the camera. Okay, so this time we have 4 outcomes, 4 phenotypes. This one is white tiger. Okay, so somebody third hour had 111, and he had 62, 20, 22, and 7. Okay, so take these numbers and throw them down here on observed. This is what you observed.
Our numbers or your numbers?
Your numbers. Yeah, sorry, not mine. Okay, your observed numbers. And then for expected, here's the Punnett square of this cross. Okay, it's a 9 to 3 to 3 to 1 ratio again. Okay, so let's plug that in. Purple and smooth are dominant. Shrunken and yellow are recessive, and then yeah. Anyway, so 9 to 3 to 3 to 1 again. So to represent that, we're gonna. So here's our 9 to 3 to 3 to 1 ratio right here. Take your total and plug it in right here. Multiply it by that fraction, and that'll give you your expected number. Just yeah, nearest whole. Just at the end, I guess, make sure it adds up to your total. So keep plugging your total in there. Excuse me. 1, 62. 21. All right, so on this particular data set, they're pretty close matches, right? So the observed and expected are pretty similar. Okay, then you're just going to run that. So observed 62 minus expected 62 squared divided by expected, that's going to be 0. 20 minus 21, we'll square it to get rid of those negatives. Divided by expected 21. .05. Same thing here, 0.05. 22 minus 21 squared divided by 21. 7 minus 7 squared divided by 7. Okay, so my chi-square value is 0.1. And we'll work on 40 a little bit, but on 40, cross this table out. There's these other ways to do the tables, but I want you to use your pink sheet one. Just get used to that. And these ones will be a little different. They're, here. Well, yeah, this will be kind of similar. And then we have a couple that are just two outcomes, right? Black-eyed lizards, yellow-eyed lizards. Question, thanks. Okay, so on that last one, there's some terminology. This good and poor fit, I'd rather you not use that terminology. What I want you to get used to is, are you rejecting the null or are you accepting the null? So again, if you reach the number, if your number is greater than or equal to that 7.81, you reject it. Okay? If your number is less than 7.81, you accept that null. Okay. Anyway, the good fit would be equivalent to rejecting the null. But yeah, I had this shoes example and it's kind of a mess. Oh, can't even see that. Sorry. So, yeah, reach the number, you reject it. Don't reach it, you accept it.